instruments. So, first question for those that are here today, because not a lot of people are here today. So, can't pick on Isaac. I mean, first day he's missed in like ever. Aiden, who should we pick on? Not Isaac. Ella, whose grave is this? There are clues in the pictures.
Yeah. Is it Galileo?
It is Galileo.
Hey! Look at you guys.
Got it in one. This is the grave of Galileo Galilei in Florence. Photography credits will go to a one Dr. Osborne. I took these pictures myself. But if you look at this part, you can see what we now call the Galilean moons around Jupiter, which Galileo was able to see because he sort of invented the telescope. I mean, there were people that had kind of telescopes before, but Galileo did it, refined it, got popular, got famous for it. So yeah, those were actually called the Medici stars. Actually, to begin with, the Medici family were his benefactors. The Medici family was also the first mafia family. So the mob helped kind of fund the development of the telescope. The things you find out from history. But yeah. Interesting things. If you remember Galileo, because not everything orbited around the Earth. The Catholic Church was not so happy with him because, oh no. So they actually had to hide. This is a later tomb for Galileo. When he first died, he was kind of on the outs with the Catholic Church, and they kind of buried him in the church in the middle of the night, hid his body. So afterwards, when Catholics are okay, Galileo, fine, not everything revolves around the Earth. They gave him a more opulent burial place. But yeah, those are the Medici stars, more commonly known today as the Galilean moons. So we're talking about microscopes. We're talking about telescopes and how to use lenses to see stuff, to see good stuff. I mean, where would medicine be without microscopes? We'd probably still be like putting leeches on people and like, oh, sure, this will suck all the nasty stuff out of you. And your blood too, and kill you if you do too much. So microscopes generally have two optical elements. We have an objective lens, and we have the eyepiece. Now, if you look through many microscopes, you know that it seems like they should have a lot more stuff to them than just two lenses. But you can make a microscope with two simple lenses. There's a trick to making it work, though. The distance to the image from the first lens and the distance to the object of the eyepiece have to match at the same point. So if you went through and put a piece of paper right there at that first distance to image, you would have your little image of the bacteria or the protozoa or, whatever the virus that you're trying to look for. if you put your piece of paper there, that would be your image. But in a microscope, we don't actually try to make the image there. We let those rays continue on past that image point into the second lens. So it still acts. It acts like there's a light source there because all the beams are going through that point. They would stop if you had a piece of paper, you'd have your image. But since there's no piece of paper there, they continue right on through and just act like a light source for the second lens, the eyepiece, that then focuses it back towards your eye to make it look like you have a gigantic bacteria or whatever else you're trying to look for. Now, remember, your original object was this one up here. Tiny. But that's what microscopes do, is they take very small things and make them look huge. So we can actually, with our visual acuity, be able to look at them, to be able to see like, oh, look, there's details. There's a cilia, there's this little thing that whips around and it moves, helps it move around, and all those are the kind of good things that we can learn from biology. We're doing it because the apparent object looks huge when we do all the ray tracing. So, objective lenses have magnifications oftentimes anywhere from 5 to 100 fold. So, if we have an objective lens that has a 5x magnification, it's going to make things look five times bigger than they naturally are. For a bacteria, is making it 5 times bigger really going to help all that much for human eyes? No, we need to have some significant magnification here if we're going to take these tiny little things and actually see any kind of usable detail on them. So generally we have different objectives, but a lot of microscopes you can actually swap out the objectives. Some have it on a fancy little thing that you can rotate, keeps everything in alignment. But you can go from a small magnification and go like, oh, okay, this is the part of the slide that I want to look at, and then go to more and more magnification and keep zooming in on what you're trying to do. Then you have the eyepiece. The eyepiece also provides some magnification. Normally the eyepieces are more moderate in the magnification. A lot of times they're maybe 10x. Sometimes I've seen 20x. The more magnification that the eyepiece tends to provide, oftentimes the smaller the opening in the eyepiece. So have you ever seen a microscope that has like the eyepieces are like 1 inch pieces of glass, and you're like, whoa, wow, I can just kind of glance in there. I can see whatever I'm looking for. Or a telescope where it's this really tiny opening. Well, the telescope, they're trying to eke out extra magnification by putting extra magnification into the eyepiece itself. So, but the overall magnification is just the product of the objective magnification and the eyepiece. Magnification. So simply multiply those two together and you have the overall magnification of your object. So let me go back in here and talk about this a little bit. So how many people have used a microscope? Everyone? Okay. Just asking. I have had occasionally somebody like, nope, never used a microscope before in my life. It's like, okay, well, don't want to make assumptions. The microscope that you used, or if you've used multiple microscopes, did all of them come with some sort of a light source on them? Why do we have a light source on a microscope?
Make it easier to see.
Okay, makes it easier to see.
You also want to like bounce the image a little bit better.
Okay. There's something kind of particular I'm looking for here. So if we have a little bit of light hitting our tiny little object, how much light can reflect off of bacteria? Probably not that much. So in order to go through and have the giant bacteria and actually have enough light so we need it big enough to be able to see the detail, but we also need light coming from those details to be able to see them too. Like, ooh, wow. There's a giant lizard attacking the city in the middle of the night. I assume it's there. You know, if there's no light, you can't really see anything, no matter how big it is. So we need enough light coming from all points of this giant bacteria so that we can actually see those details. It's not just black. So we go through and illuminate it. We illuminate it with actually usually fairly bright lights. And then we can not only have it large enough to see the detail, but also bright enough that we can actually see the detail. But illumination is one of the things about microscope design that we're going to talk about in some depth today. But before we get to that, we're going to talk a little bit about objective lenses. And objective lenses in a microscope are usually measured in terms of numerical aperture. So numerical aperture is just the index of refraction and the sign of the kind of half angle here. So the theta is the entire kind of angle. Alpha is just half of that. So if we're going to gather a lot of light, we would probably want that alpha to be as large as possible, wouldn't we? I mean, if you look through a pinhole, you're not going to get a lot of light through that. You want a large viewing angle. And if you get all the light from this large viewing angle, you're going to get a lot of light in. Well, there's a problem with that. Is that this viewing angle, a lot of times there's a physical limitation about how close the objective can actually get to your sample. I mean, unless you actually put the sample like on the objective. We don't normally do that, do we? We normally put it on a microscope slide. So if we think about this angle, there's kind of there's some trigonometry in there. There's kind of a minimum thickness that we can get away with, isn't there? Because we need that cone, the point of that cone, the focal point of that cone, to be not inside the glass, but inside the sample. So, yeah, we're kind of limited on what we can do and how much light we can gather by how thick our microscope slides are. Traditional microscope slides, maybe a millimeter thick. When I was in when I was doing my research for my PhD, we were using really high numerical aperture lenses. Numerical apertures of like 1.45 are very, very wide angle. But we also had to use, instead of using microscope slides, we actually used the little microscope cover slips. And those are super, super, super thin. There was a group just across the hall from us that even those microscope slide covers, the super, super like flimsy, like you're worried when you try to lift them because they might just snap in your fingers. For the group across the hall from us, that was too thick. That was too thick. They built their samples on a single layer of mica. So they would go through and like use sticky tape and put it on a piece of mica and lift it, and it would break off just like a few atoms thick layer. And that was their microscope slide that they used. So they could get even higher numerical apertures so they could get even more light gathering capabilities. So there's some trade-offs here. There's some physical, geometric issues that kind of limit how far we can go with this. But generally, the larger the numerical aperture, the more light gathering capability you have. And something like a 1.45 is an incredibly high numerical aperture. I think that's as high as I've ever worked with myself. There probably is a 1.5 or 1.55 out there too, but 1.45 I think is as high as I've ever worked with. F number. So the F number is, again, a photography term. So, I mean, we had our microscopes. Now we're jumping to cameras a little bit. Then we're going to go back to microscopes. But your F number is about 1 over double the numerical aperture. But it talks about the light per unit area reaching the image plane. And yeah. But again, more of a photography thing than a microscope thing, I think. Okay, so illumination. I feel like I should have, yellow skin and blue coveralls if I say illumination. Minions reference, yes. Okay, so here are some common illuminating methods. And we'll start off with, just dark field and confocal. So this one is kind of your traditional biology microscope kind. So we have our specimen, we have our objective, and we have a light that's shining basically through the sample into the lens. If you have a very thin sample, that works pretty well. Even if you have a kind of a thicker sample, light will bounce off one thing and bounce off another. It'll scatter, and there'll still be plenty of light that comes into the objective. What's the problem with this? What's kind of the fundamental issue with your basic kind of biology microscopes, that the light is being focused into the sample and into the objective? What's that? Not so much that it bounces back in, but you're staring into the light. I mean, your eye is up here. You're looking at the objective. That light is shining right into your eyes. It works, but it also kind of limits you. If you're staring into a spotlight, Like, yeah, I can kind of see. Concave mirrors, these are kind of the next step up, but they still have the same issue. You're still staring into the light. I mean, is it a biology class or is it a police interrogation? I don't know. But they have you under the spotlight. You're trying to see as you're looking through this. So how can we do it better? Well, one way is called dark field illumination. So we have all this light going into that same kind of lens, but part of the lens that would actually go right into the objective is kind of blocked off. So the light that's coming in is coming in from the side, or this side. Well, it still comes in, it still hits that bacteria, the sample that we're dealing with, scatters around, things still get illuminated. But you're not steering directly into the spotlight to try to make it happen. Dark field illumination is very much like a solar eclipse. The moon goes through, it blocks the sun. If you just stare directly at the sun, it's really bright. You can't always see as much detail. The moon goes through and covers the sun. Can you start seeing detail there that you didn't see a few minutes before? Yeah. You're not staring into the bright light anymore. So now all of a sudden some of the more subtle detail starts showing up. And that's what happens in a dark field illumination microscope. And then we have my favorite, because this is the kind of microscope that I used in my research. This is a confocal microscope. So, confocal. It means that the light and that's traveling to the sample and the light that's coming from the sample travel the same path. So I have light coming in. So light coming in, it hits a mirror and goes down to the sample. That sample is going to go through and be excited by it. And let's say the light coming from the sample starts coming back up the same way. And it hits a mirror. Now this says it's a plain glass reflector. Yeah, okay. So the way your book describes it, this would be like what we call a two-way mirror. And who can tell me what a two-way mirror does?
It reflects the image on one side, and then while you're on the other side watching through.
Absolutely. So we're talking about police interrogations. You're in the interrogating room. The detective's grilling you. They have the light shining in your eyes. Tell the truth. There's this big mirror on the wall over there. You just see yourself. It looks just like a regular mirror to you. People on the other side can see through it. So in this particular case, we have the light coming in. It hits this. It looks just like a regular mirror and reflects. The light that's coming from the sample is getting collected by the same objective. Some of that gets reflected, but some of it passes back through on towards the eyepiece. Now, in my experiment, I used laser light for my excitation, So lasers are very monochromatic. They just have one color. Generally you just have one color. So I used a mirror that reflected just that one color and let all the other colors pass through. When we talk in the next chapter, we're going to talk about thin films, like why soap bubbles look all rainbowy and stuff like that. We'll talk about that in the next chapter. But that same kind of idea, that same kind of technology can be used to create really interesting mirrors. Mirrors that will reflect one wavelength and let all the other wavelengths pass through. That's the kind of mirror that I used. So my laser light was all getting reflected, and even if my laser light hit the sample and came back, it was just going back towards the laser. I didn't care. And every other color, other than my laser light, went through that mirror towards the eyepiece, and I was able to go through and collect all my data and do all that kind of good stuff. But this is confocal. So the light's getting focused onto the sample by the objective, and the objective's also capturing the light coming back off the sample. So it travels the same path going out and back in. But yeah, I like confocal microscopes. If they didn't have confocal microscopes, I would have done something else for my PhD. But I did a lot of work for my PhD on a confocal microscope. So, again, kind of the biology lab technology, the advanced biology lab, and I think we actually have a confocal microscope or two running around somewhere on campus. But this one, confocal, tends to be a little bit more for the specialized applications. Okay, so that's microscopes. What happens if we want to look at something farther away? Well, we have telescopes. We have Galileo's little invention here. So telescopes come in kind of two forms. We have the convex concave. So this is the kind that Galileo came up with. And specifically, because it has a convex and a concave, you'll end up with a non-inverted image. So you look through the telescope and things will look right side up. The green part of the trees is up, the brown part of the trees is down, the way the world's supposed to look. So to do that, generally we have our convex objective, and then we'll have a concave eyepiece, or a converging objective and a diverging eyepiece. But if you do the ray tracing, you can see that, we can go through and see that object, that little piece of tree there also now starts looking like a much bigger thing. It looks like it's a lot closer to us, and that's great. But convex or diverging lenses are not always the simplest ones to make. It's actually a little bit easier to go through and make two convex lenses. And just like what we had with the microscope, so we have our light coming in, light coming in, light coming in. We have the image from that first lens is the distance to the object, a little air quotes going on, object of the eyepiece. So again, for the eyepiece, it can't tell any difference as to whether there's actually an object there and light's coming off of it, or whether light's coming through that plane that acts as though it were the image plane. This lens can't tell the difference. It's light going in different directions, and it all looks like it's the same thing. But as you do the ray tracing, even if the object is very far away, you can make it look a lot closer with a telescope. Slightly upgraded telescopes will actually have a third lens in there. The lenses were not easy to make in Galileo's time. We talked about, astigmatism. If you get things ground not perfectly symmetric, you get a little, carnival mirror thing going on there. Good lenses are hard to make. They're a lot easier now. But still, if you buy a $50 telescope at Walmart, you're not probably going to get great optics. They're probably going to have a little bit of wonkiness to them. But if you go through and you use a third lens in there, what we would call an erecting lens, in telescopes, sometimes they're called Barlow lenses. We'll go through, if you have like a 1.5 or a 2x Barlow, those will usually flip the image right side up, so that if you're looking at trees or birds or something, the bird isn't hanging upside down like a bat would be. It looks the way you would expect, and for some people that's worthwhile. That's worthwhile. But again, in both of these cases, where the image of the previous lens happens is where the object appears for the lens right after, and vice versa. The image for this lens is where it perceives the object for the eyepiece. So those are lens-based telescopes. When you start getting into bigger and bigger telescopes, we tend to switch to mirrors. Mirrors are generally easier to make than lenses. So really big, really affordable telescopes are just simple reflectors. They have a large mirror that's a focusing mirror at the bottom. Usually they'll have some smaller mirror that's the redirecting mirror. So that is that one over there. And then an eyepiece to do that final kind of focusing for you. But those are big. Those, I suppose you could disassemble it, but then you'd have to realign it. Who wants to do that? I want something that's going to fit in my car so I can just drive and just take it out and set it up easy. That's where we get into compound microscopes. Like this one. Common type is what's called a Schmidt-Cassegrain. And a Schmidt-Cassegrain will have a large lens in the front. We'll have a focusing mirror in the back end of the tube, so that as we go through, so if I'm drawing this in kind of diagram, I would have a lens. Should be able to draw a better lens than that. Okay, lens. There we go. That's a little bit better lens. I'd have the tube. I would have a mirror, a focusing mirror down here. So this is focusing mirror. I'd have a lens. I would also have another focusing mirror. And the way the light would come through, trying to figure out a color, green. So the way the light would come through is it would come down, get focused by the first lens, bounce off the bottom lens, get focused, would hit that smaller focusing mirror, get focused, and then would go out through the eyepiece. So it's making multiple passes through that tube, which is why this one is so short compared to something like that. The simple reflector that telescope is probably taller than I am. This Smith Cassegrain is probably about that long, maybe 18 inches long, roughly. And then there you can actually see the eyepiece there. There's a little mirror to make it, bounce back up, so you don't have to sit down on the ground to try to actually look through it. But yeah, basically, that's how a lot of amateur telescopes actually work. And if you actually look, let's see if I can blow this up a little bit. Blow this up a little bit. You can actually see right there is that second kind of focusing mirror. If I get rid of it, you can kind of see there is something kind of stuck in the middle of that. That's that second focusing mirror. So, yeah. Mirrors are cheaper. Mirrors are nicer in many ways. Probably the biggest problem with mirrors is that a lot of times they're temperature sensitive. So they'll expand or shrink with temperatures. So you kind of have to let them cool off, get to the air temperature of the night sky or the night air. So they can be a little fussy. Don't take them out of a warm car and set them up and expect them to work right away. They do take a little bit of time to kind of find their balance. But after that, they work pretty well. Aberrations. Just a couple more slides to go through. There are chromatic aberrations, which we kind of talked about when we first started talking about lenses and focusing. Chromatic aberrations are simply that different wavelengths of light have different refractive indices. So they'll bend a little differently. If you're trying to use a prism to make a rainbow, that's great. If you're trying to, look at a tree and all of a sudden it's this weird, Joseph's coat of many colors tree because all the colors get separated, it looks a little weird. But oftentimes you can go through and use multiple lenses so that one's making it, separate one direction, one's making it separate the other direction. They kind of cancel each other out. And you can actually end up at least the focal point with something that looks like the right color. That's the white light. But you have to work about designing them properly to make that kind of stuff work. There's coma is another type of aberration. And that's where objects off-center will tend to make a pear-shaped image or a teardrop-shaped image. Even good telescopes. I mean, I don't have like a super expensive telescope, but I have a decent telescope. Even decent telescopes, if you look at things where they're off-center, a lot of times they'll be slightly distorted. Even good optics can have coma. So your least amount of distortion is going to be right as you're going right through the center of that lens. But wasn't that one of the assumptions we made with the thin lens equations to begin with? That if you go right through the center of the lens, you're not going to have any kind of shift. It's going to be great. It's going to do what you want it to do. So if you point your telescope where the object that you're looking at is right in the center of the field of view, the least amount of distortions you're going to get. And then spherical aberration, if you have a spherical lens rather than a parabolic lens, it's going to focus weird. The outsides are going to focus at one spot, the rays that go through the center will focus at a different spot, and you'll never quite get it into a sharp focus. It'll be kind of a focus-ish range, but it'll never quite get to a really sharp image. But that's spherical aberration. Again, spherical optics are cheaper optics. That's more your $50 telescopes. Cheap binoculars can also have this go on as well. But you start getting into the higher end stuff, and it doesn't even have to take like super high end stuff. If you started getting $100 pair of binoculars versus a $25 pair, you're probably not going to have a lot of spherical aberrations. So it's not like you have to do like, $10,000 pair of binoculars. No, just a little bit more than the cheapest version. You're probably getting out of a lot of the spherical type optics. Those are really kind of saved for the cheapest varieties of most of what we're doing. But for some people, that's all they want, you know. They just want to be able to see from a distance, and focus isn't perfect. It's good enough for me, and they go on. Okay, so real microscope objectives are usually quite complex. So it's not just a single lens like we've been drawing for the objective. Usually it's multiple lenses. They're often paired. They have different materials that they make these out of, trying to go through, and this is going to have a chromatic aberration in one direction. Well, we're going to go through and have another lens that's mirror imaged of it, that's going to reverse that, so everything stays where we want it to. Even going through and looking at some of these, they're all just kind of complicated. So what we draw for, look, this lens is my eyepiece or my objective lens. They're more complicated than that, primarily because of the aberrations that they're trying to avoid. And lastly, hypercentric optics. Has anyone ever played with any of those 360-degree cameras? You know what I'm talking about? Okay, so they have cameras. Several companies sell them. There was one by Samsung that was really popular for a little bit. But basically, you could take like a 360-degree panorama with something that was a little bit larger than a GoPro. But it had two lenses on it. One that had this giant lens on the front and a giant lens on the back. But if you look at, so this image was taken from I think a patent application that I found. I was like, this actually shows how these things work. So I stole it. But this is what's called a 270-degree fisheye. So 90 degrees is about like this. It can see from this hand all the way around to the other hand. It can see 3/4 of a complete panorama just with one lens. But if you do the ray tracing and all of this, you can see that even this light that's coming from behind the camera would hit that lens. It would refract, and it would keep getting bent until it came back to the sensor. The Samsung camera wasn't quite this extreme. It had two 180-degree field of views. And there was this kind of weird little scene in the images between them. You could kind of see like, oh, hey, that's where I switched from camera 1 to camera 2. Look. But, I assume Facebook still probably supports them. But for a while, they were the big thing on Facebook. You could upload that, and you could scroll on the picture as someone was riding their mountain bike down the mountain or whatever. You could scroll and look off to the side as they're going down, or behind them as they're going down, all off the same video. But just two different lenses. One in the front and one in the back was all they actually needed with these kind of hypercentric optics. So very, very niche use. This isn't something that you're going to run into necessarily every day, but Yeah. We actually, okay. 30-second rabbit trail. We actually thought about getting one for the campus when we dedicated this building. And what we were going to do is we were going to go through, like I said, it was a big deal. I don't see them so much anymore online, but we were going to go through and do virtual walkthroughs of all the buildings on campus. And basically you put the camera on a stick on a remote control car or something, and just have it run down the hallway, and it's going to do that. So if people want to stop and like, oh, I want to see inside that classroom, you can scroll over like, oh look, classroom, and now I'm going this way. The biggest reason we didn't do it, because the camera wasn't that expensive, it wouldn't have taken that much time. Someone was like, just in case there's an active shooter, do you really want to go through and have this map of your entire campus that they can just like see every little nook and cranny? And they're like, yeah, okay, that was a bad idea. But we thought it'd be this really cool, like, oh, look, you can actually see and pretend tour of the campus and everything else. And they're like, yeah, but if you put it on the internet, people could use it for whatever they want, and yeah. So we didn't actually do it. But this is the kind of optics that would have been involved if we had actually done that. But questions about how microscopes or telescopes work? I will tell you, so the one thing that I will say is often missed, often overlooked in student descriptions and sometimes conceptual questions on the test, is that the image from the first lens has to be the object for the second lens. Though these lines have to match to the point of those lines. Not telling you necessarily how I'm going to write the question because I haven't written the test yet. But I do see that a lot where people will just say, oh, there's two lenses and it magnifies. And it's like, yeah, but what actually makes the two lenses work is that they cross at that image plane right in between. That's what makes microscopes work. That's what makes kind of your more common telescopes actually work. It's an important part to it. So just putting that out there, that it's a good thing to like make a little note on your study guide. Like, oh, okay, yeah, that the DI and the DO, are crossed at the same point is kind of a big deal. But other than that, I'm going to go ahead and call it there for the day. I'm going to call it there for the week. I want to call it there for the semester prior to spring break. Have a good rest of your spring break, and we will catch you on the flip side.